So we did this with quadratics. We're finding the roots. Where do the pieces of the function, when we substitute in a value for x, where does that turn the whole thing into 0? So this uses the zero product property, which just says, if we multiply by 0, everything becomes 0. Everything becomes 0. Okay, we're going to get a bunch of coordinate points that we're going to graph. Coordinate points. And these are all going to be x comma 0. They're going to be on. So if we have our, x and y axis, they're all going to be on the x-axis. They could be all over the place. There could be a bunch of them. There could be a few of them. For quadratics, when we did this, there were either none, like it didn't cross the x-axis at all, or there was one, it just crossed it like 1 point, or 2. For polynomials, because there's more solutions, there's more than 2 possible. What was I saying? Because of that, there's multiple points, because there's more solutions. Okay, for polynomials in particular, the number of solutions matches the degree of the function. So if you remember back to the beginning of the unit when we talked about the leading coefficient and the degree being the biggest exponent, the number of solutions is directly related to the degree of the function. Now, they might not all be real solutions. Some of them might be imaginary. We're going to kind of ignore the imaginary solutions, but it is possible that there would be, there are equations that we're going to try to avoid that have imaginary solutions. Okay. I'm sure there's a theorem for that one. I don't remember what it's called. Nope. Yeah, I'm recording right now. Yep. So, for example, for this specifically, x squared minus 9 has 2 solutions. X equals 3 and x equals negative 3. Right? If I factor this, I get x minus 3 and x plus 3. And so then x equals 3 and negative 3 when this is 0. Ignoring how we get those numbers, we'll come back to that. Because it's x squared, it has 2 solutions. If we had a higher degree function, like x to the 4th, it's going to have 4 solutions. It is unknown until we solve it, until we factor and solve it and find the solutions, if those solutions are real or imaginary. So some of those might be imaginary. might be imaginary. We're going to ignore those, okay? But I do want to show you what those solutions would look like. So I'm going to switch to Desmos here, and we're just going to look at some different graphs. Okay. All right, so we had x squared, oops, minus 9, right? And so these are two solutions. This is where the graph crosses the x-axis. We have an x value, and then we have a y value of 0. Now, that's all fine, but what if we, increase the degree here? Well, this has one real solution, and we wouldn't do this problem because the solution is not an integer. And then it's going to have an imaginary solution. It's got this little curve right here, like in a cubic function. I guess this is a cubic function. That has imaginary, this means that there are imaginary solutions. One real solution, and then two imaginary solutions. Okay. Now we're mostly going to do functions that look something like this. Okay, so this function, it goes up, and then it goes back down, and then it goes back up, and it crosses 3 times. It has 3 solutions, and those would be where these things, each of these parentheses turns into 0. Okay. If I add a, let's see, x squared plus some number. Okay, not only does this like stretch it out, but now it's got this kind of weird, like this part of the function right here is not what we would expect in terms of like curvature. It's got like it's not perfectly round. That's because this has an imaginary solution. It's x squared plus some number, right? So to make that equal 0, we'd have to subtract and then take the square root, and then we get a square root of a negative, and so that's an imaginary solution. Sometimes they're more pronounced. We're mostly going to ignore this kind of thing and not have problems that include those imaginary solutions. Okay, this is another one that we might have, something that looks like this. And so we have a solution at -1, we have a solution at 0, we have a solution at 2, we have a solution at 4. Okay, this is just stuff we might run into. The other thing that we're going to do, that we're going to come across when it comes to solutions, is a multiplicity. And so we'll write this in our notes in a second. But a multiplicity is just when a solution happens more than once. So if I have x squared, that means that I have 2 solutions that are the same that are 0. Right? And so at 0 here, you'll notice something different happens than what was happening at -1 and 2 and 4. Instead of crossing through the function, instead of crossing through the x-axis, the function now bounces right here. Right? And that same thing could happen at any of these other points. If I square x minus 4, not only does the function get steeper because now we're squaring bigger numbers, it bounces at the 4. And it might bounce over here too, at 2. And so now here at both of these, the function doesn't pass through the x-axis, it bounces back up. And that's because this is an even degree multiplicity. It's a multiplicity of 2. If I change that to be a 3, well now at 2, where there's this cube, x minus 2 cubed, instead of bouncing, it goes through that point, but not like a straight line. These aren't straight lines. they just look like it. But now it looks like a cubic function where it's got this little squiggly. Okay. And we could change it to a 4. That's going to look like a 4th degree function right here, as opposed to more like a quadratic. And if I change it to a 5, it's going to look like a 5th degree function. Okay. So odd multiplicities will still pass through. They'll just be curvy. Even multiplicities, like repeats of the solutions, are going to bounce. But the higher degree ones will be, they will look wider. So like if I put a 6 here, notice how it's getting wider every time. It's like stretching. Versus a 4 or a 2 or even an 8. Okay. Now, because we're looking at big exponents, these functions are going to get large really quickly. Right? So it looks like these lines are really vertical, and they're not. It's just that I have to zoom out really far before I see the loop back. Right? And so it looks like these lines are vertical, but that's just because I have an 8th power here. So this is like a really big function. If I work with smaller exponents, then the curves become more clear. And so when we're actually graphing, which we're not going to do today, we're just going to find what are these points. When we're actually graphing, I don't care how far down you make these peaks and these valleys. I'm not worried about the accuracy of like, are you finding this point? We're not going to talk about how to do that, how to find the maximums. We just want to find the roots and get the directions of the graph correct. Okay. So that end behavior stuff will come in later. Today, we just want to find, okay, what are these coordinate points? Okay, so multiplicity. Let's write down what I said. These are just repeat solutions. So we're going to factor, and we're going to get like, you know, x minus 3 squared. We're going to get 2 copies of x minus 3. This would be the same as x minus 3 times x minus 3. Or we might get 3 copies of something. We might get an x cubed. This is, you know, x times x times x. We have a repeat of 0. This would be a 0, right? 0. Putting 0 in here turns this into 0. This is going to be a repeat of 3. Okay. Even multiplicities, or even degree multiplicities, even amounts of them, bounce at the root when it comes to the graph. Odd ones, so a multiplicity of 1, only having 1 copy, is just going to pass through. And we'll talk about this more when we actually start graphing. But for now, just be aware that you might get copies of the same thing. You might get x cubed as a greatest common factor. You might get x minus 3 squared after factoring. Okay, so it may be that we come up with multiple copies of the same thing. Okay, so in practice, what are we actually doing? We're going to factor the polynomial completely as far as we can. It may be that we run into stuff that's not factorable. That's probably means that there's an imaginary solution somewhere, and we're just going to leave that alone. We're not going to use the quadratic formula. We're not going to take the square roots of negatives. We're going to ignore imaginary numbers, even though it's possible to run into those. We're going to factor completely, and then set each parenthesis to 0 and solve. So usually this just means it's going to be the opposite number of whatever's in there. But sometimes we're going to get fractions. Okay? The warm-up problem that we did is going to have a fraction in it. Whenever it's 2x or 3x inside of our parentheses, and not just a greatest common factor, we're going to get a fractional answer for our solution, and that's okay. We will do fraction answers. We're not going to do irrational answers, which means we're not going to do square roots or decimals that repeat, but you might get like 1/3 or 5/4 or something like that. Okay. So let's actually do this. Let's factor completely and then set equal to 0 and solve. So this is going to be our continuing on of our practice yesterday, or our factoring yesterday. We just have one step at the end. Take the parentheses, take whatever you get, and equal to 0. Before we actually do the factoring, though, I'm just going to throw some already factored examples up, and then we'll find the solutions for those. Let me know if you need more time with that page, because I think we should be good. Okay. So find the solutions of the polynomial. I'm not going to rewrite these instructions, so we're going to have a couple problems. F of x equals 3x squared times x minus 5 times x plus 2. Okay, so when we're finding solutions, that means we're going to set the whole problem equal to 0. We did this with the quadratics too. Whole thing equals 0, so 3x squared, x minus 5, x plus 2, all that equals 0. And then, well, since all of it equals 0, if each individual piece becomes 0, if this becomes 0, then I'm multiplying everything by 0. And that means that's a solution. So this right here, this piece, let me use a different color. Which means we get x equals 0 with a multiplicity of 2. We get 2 copies of x equals 0. We don't need to write x equals 0 more than once, but we do, when we're graphing it, need to remember that this is a multiplicity of 2. We have 2 copies. That one's easy. The x out front, always, if there's a greatest common factor with a variable in it, we're going to get 0 as one of our solutions. Okay, and so that would actually give us the coordinate point 0, 0. Or little face. Okay, this next one, I think pretty quickly we're going to get into the habit of just taking the opposite number. But what we're saying is x minus 5 equals 0. When this parenthesis is 0, well, then we're multiplying this thing by 0, and we're multiplying this thing by 0. And it all turns to 0, which is what our goal is. And so what number turns this x minus 5 into 0? Well, we add 5 to both sides. We get x equals 5. I don't expect you to write this equation out every time. You can say, oh, what's the opposite thing? I'll talk about that in a minute. So this gives us the coordinate point 5, 0. That's one of our solutions. And then this last one, it's the same thing. We have a x plus a 2. So we take this thing and say, okay, x plus 2 equals 0 when x is -2. Which means we get the coordinate point -2, 0. So those are our 1, 2, 3 solutions. Really, it's 4. So we should have the same number of solutions as there are x's. So there's 1, 2, 3, 4 x's here. The x squared counts as 2. Remember, there's a double solution right here at x equals 0. Okay, if we graph this, so we had 3x squared, x minus 5, and x plus 2. If we graph this, we get this function, right? And so we have the solutions of -2, 0, we got that one. 0, 0, we got that one. And 5, 0. And you'll see the graph here doesn't pass through 0, 0. It bounces right here because we have an x squared. We have a multiplicity of 2. So those are our solutions. If we multiply our original equation out, right, multiply these two binomials, get a quadratic, then multiply everything by 3x squared, we're going to get 3x to the 4th as our first leading term. Which means there should be 4 solutions, and there are. We have 1, 2, and then this one counts twice because it's an x squared. So 1, 2, 3, 4 solutions. Okay. We did this back with quadratics. We said, all right, what are my solutions? Where does x equal 0? What turns the equation to 0? The other thing I want you to remember is that when we do our synthetic division, we say, okay, I'm going to divide whatever this polynomial is by like x minus 5. We get 0 at the end because it's a factor. But also, we're swapping the number out, right? If I was to do synthetic division for this polynomial with x minus 5, I would use positive 5, and I would get 0 at the end. Positive 5 and 0. Those are intrinsically linked because evaluating is the same as the dividing, right? We're evaluating the function at 5. When we evaluate this function at 5, we get 0. Hopefully that makes sense. I'm not going to write all that out, but I want to connect the evaluating with the synthetic division. Okay, let's do another one of these. B, g of x equals let's see, let's do an x and then 3x plus 4. Okay, a couple differences here. We have a polynomial squared, right? The x minus 3 is squared. We have 2 copies of this. And then we have this thing, which has a 3 inside the parentheses times the x. So I'm going to rewrite this as it equals 0. You don't really need to do this step when we're finding solutions. It's a bit assumed that the whole thing equals 0. But this is what lets us use the zero product property. Because the end is 0, that means each of these products can be equal 0 individually. Doesn't mean they're all the same, it just means individually we could set them equal to 0. So this x here, and you don't need to draw these arrows every time either, but this x means that we get x equals 0. All right, if we multiply 0 by everything, it all turns to 0. This x minus 3 means we have a means that when this equals 0, we get x equals a positive 3. But there's a multiplicity here. We have 2 solutions at x equals 3. Not really concerned about that right now. I'm just trying to reiterate it. Now, the last piece here is maybe the hard piece. Hard. Take this thing. Before for this one, this x minus 3, I just need to think in my head, okay, what minus 3 equals 0? 3. 3 minus 3 equals 0. And so I don't really need to write this algebra step out. I can just say, oh, x equals 3. For this, though, we're saying 3x plus 4 equals 0. We're going to need to subtract and divide. And we're going to get a fraction. Subtract 4 from both sides. We get 3x equals negative 4. Divide everything by 3. And so x equals negative 4 thirds. We get a fraction. So we have 1, 2, 3, 4. This one counts twice, solutions. 4 solutions. And we would write those as coordinate points. So we'd get 0, 0. We'd get 3, 0. And we'd get negative 4 thirds, 0. Okay, I want to do one more like this with imaginary solutions. We're not going to find the imaginary solutions. I just want you to see what you might run into, and then you'd say, oh, I'm going to stop attempting this problem because we're at imaginary solutions. I think you're most often going to run into this after you've factored by grouping. It's possible you get something like this. All right, so for both of these, when we're finding the solutions, I'm going to take each piece, set it equal to 0. That's where we're going to find our solutions. For this 2x minus 1, I'm going to add 1 to both sides. We get 2x equals 1. Divide by 2, so x is a half. So we have 1/2, 0 for one of our solutions, or 0.5, either way. But this over here, we're going to get x squared equals negative 4. And then to get rid of the square, if you remember back to like December, take the square root of both sides, and then we have the square root of a negative. This is imaginary. So there's going to be 2, because it's x squared, 2 imaginary solutions and 1 real solution. And so we ignore this. We're not going to find those. We have the tools to. We talked about it last semester, but I don't want to spend time doing that. Okay. And what this looks like, if I graph it, we've got a 2x minus a 1. That's going to go through a half, 0.5 comma 0. And then we had x squared plus 4. Now this looks pretty weird. It doesn't really look like much at all. But that x squared minus 4 gives it this slight, or x squared plus 4 gives it this slight curve. Just because there are imaginary solutions does not mean that it's not a real graph. It's a real graph. It's just this x squared plus 4 part, where that curve is, it's really kind of impossible to see where that curve happens. Where that curve is not on the x-axis, and so we only get the one solution, and then two imaginary solutions. This, if we multiply it out, gives us an x cubed. There are 3 solutions. 2 of them are imaginary, we don't care, and 1 of them is real, this 0.5. We're not really going to give you problems like this. I just want you to see it because it exists. Okay, so that's how we find our solutions after we've factored. The expectation, though, is that you factor it yourself and then find the solutions, right? So we'll have to factor some stuff by grouping, finding the GCF, using all of our other tools. Okay, so we're going to do a couple of those. Time permitting, hopefully. Oh yeah, yep, sorry. Like that. So I'm going to start a new paper, but I'm just going to start it underneath this so that we can have both those things up at the same time. Yeah, that should be fine. Okay, so fully factor and solve. We've got x cubed plus 2x squared minus 9x minus 18. There's no greatest common factor here. Each term doesn't have something in common. You're good. Cool. Each term doesn't have something in common, but we have things in common with the pairs. So we're going to factor by grouping here. So we check these two things and these two things for what they have in common. You take an x squared out of the first two, left with an x plus a 2. And then I can divide both of these by negative 9. So we get x plus a 2 again. So this is x squared minus 9 times x plus a 2. So we factor by grouping. Now we're not done factoring because this is x squared minus a 9. And so we need to factor that piece. That piece has an a value of 1, a b value of 0, and a c value of negative 9. When b is 0, really we're just looking for the perfect square here, and then we need a positive and negative. We need two numbers that multiply to make negative 9 and add to be 0, which is going to be 3 and minus 3. So this whole thing is x minus a 3 times x plus a 3 times x plus 2. So that's fully factored. Here we use the Xbox method, or it's the perfect square pattern. X squared minus a square means that we're going to get x minus 3, x plus 3. Now we need to find the solutions, which are just what are the zeros? What are the zeros here? So x minus 3 times x plus 3 x plus 2 equals 0. We need to find the solutions. So we're going to set each parenthesis equal to 0, and whatever number we get, that is one of our solutions. You don't need to write out each equation, but you can. So we'd say, okay, x minus 3 equals 0, x plus 3 equals 0, x plus 2 equals 0. And so we get 3, negative 3, and negative 2. Which means we have 3 coordinate points. 3 comma 0, or sorry, x equals 3, x equals negative 3, x equals negative 2. So we get 3 coordinate points. 3 comma 0, that's one of them. Negative 3 comma 0, that's another one. And negative 2 comma 0. 3 solutions. 3 values that if we substitute it into either our factored form or our original equation, we're going to get 0 at the end. Which should make sense. If I told you to factor using x plus 2, the original thing, and you did synthetic division on it, at the very end you're going to get 0, right? Because it's a factor. You're going to get 0, which is what this is saying. If we evaluate it for negative 2, we get 0. And if we do synthetic division for x plus 2, we use the opposite. We use negative 2, and then we do 0. The same thing works for our fractional solutions. You can do synthetic division with fractions. We just have avoided it. So you'll notice we got 3 solutions, 1, 2, 3. And our original equation was x cubed. So our number of solutions matches the degree of the function. Okay, and then on Desmos, our original function was x to the third is 2x squared minus 9x minus 18. And that gives this quadratic, which crosses at negative 3, negative 2, and positive 3. Yep. So those are our 3 solutions. That's where the graph crosses the x-axis. Those are the roots. Okay, should we do another one? X to the fourth minus 24x cubed minus 60x squared. This one has a greatest common factor. So the first thing I'm going to do is, well, we want it equal to 0. We'll come to that later, though. We got to factor it first. So the first thing is, let's take out the greatest common factor. The greatest common factor is 3 and an x squared. This leaves us with x squared minus an 8x minus a 20. Wait, is this not factorable? Oh, no, it is. Never mind. Sorry. Scaring myself. So we factored out the GCF. Now we're going to use the Xbox method. A is 1, B is -8, C is -20. We need two numbers that multiply to make -20 and add to make -8. So that's going to be numbers that multiply to make 20 are 20 and 1. That's not going to add to make -8. 2 times 10, those can make an 8. And so I know that it's 2 and 10. One of them needs to be negative. To multiply to make a negative and add to make a negative, it needs to be the -10. That's the negative piece. And then since a is 1, we can just use 2 and -10 as our answer. So we get 3x squared times x plus 2 times x minus 10. That equals 0. Which means our solutions then are 0 from the x squared. That gives us x equals 0. The opposite of this thing, so that means x equals -2. And the opposite of this thing, which means x equals 10. If I put 10 here, 10 minus 10 equals 0, all multiplies to make 0. If I put -2 in here, -2 and 2 make a 0, everything becomes 0. If I put 0 in here, 0 squared, everything becomes 0. And so we would get the coordinate points 0, 0, -2, 0, and 10, 0. Notice it's x to the 4th. We only have 3 solutions, but this one is a double solution. It's x squared. There's 2 solutions, 2 copies of x equals 0. Kinda. It's a multiplicity, which means that on our graph, if we were to graph this, it's going to not pass through 0, 0. It's going to bounce. It's going to make a U shape at 0, 0. I want to do one more, I think. Oh, I know what we need to do. Okay. Homework is going to have a couple things I haven't talked about yet. Sometimes it's not in standard form. So we're going to do kind of an easy one. X squared minus 6x equals, what would it be? 9? This is not in standard form. This is very important. There's an equal sign in between the pieces of my function. So we need to subtract the 9 over. These aren't like terms, so they're not going to combine or anything. But we need all the pieces of the function need to be on the same side of the equal sign. So we get x squared minus 6x minus 9 equals 0. Wait a minute. That's not going to work. Sorry. Make this negative and just switch all these to pluses. Sorry. Now it works. Then we can factor and solve. Yeah, mix up the negatives, my bad. Still not like terms, so the negative 6x and the 9 aren't going to combine. So we just write it on the line here. But then when we factor this, we're going to get, okay, two numbers that multiply to make positive 9, add to make negative 6 are negative 3 and negative 3. So we get x minus 3 times x minus 3 equals 0. This happens twice. In other words, it's x minus 3 squared equals 0. And so our solution is 3, which only gives us the one coordinate point because it's a quadratic. And it's going to bounce at that one coordinate point. But this was not in standard form originally, and we had to move it. You may need to do that. You may need to add and subtract some stuff across the equal sign to get everything on the same side so that we have a problem we can actually factor. Don't get confused when the equal sign is in the middle like this and try and do x squared minus 6x minus 9. Don't ignore the negative. I mean the equals. Don't ignore the negative either, but the equals is like a barrier. You have to have everything on the same side for you to be able to factor. Is there any other things from the homework that I wanted to mention before we were done? I think that's it. Factor out the GCFs. Factor. It should be fine-ish. Might change it to 3 through 6. Yeah, I'm going to change it to 3 through 6. But otherwise, we should be good. Should be good on the homework. Okay?